Okay, so the room is fully packed. Nice to have you here. Also nice to have Mitchell Hashimoto here. He's the speaker of the talk Automating the Modern Data Center. Most of you know the tools Vagrant, Consul, and stuff like that, and Mitchell is the creator of it. So happy that you're here and enjoy his talk.
Okay, thanks for coming. All right, so I'm going to give the talk, Automating the Modern Data Center. So in the program, it said from development to production. It won't be from development to production. It's going to just be from like production to production. So I'll explain that in a second. So I got a pretty good intro, but if you want to find me or tweet at me or ask me a question and you don't want to ask after this, or you think of it later and you can't find me, just tweet it at me. I'll be around. I have to leave tomorrow to go to another conference in Budapest, but I'll be around for all day today, so just find me. And I'm staying at this hotel, so I can't like hide anywhere. I work for and started the company HashiCorp. We use this word that Nigel said he's not a big fan of, which is software managed or defined data center. It's pretty much the same thing. But to that end, we've made so far 5 open source tools, Vagrant, Packer, Surf, Consul, and Terraform. And so this would be from development to production. But I've tried to give that sort of talk before, and it just doesn't fit into an hour. So you end up walking away really not learning much of anything. So instead, I modified the talk to really just talk about more of the production side of things, which seem to be more interesting right now for a variety of reasons. This is sort of the area within HashiCorp's tool growth that's seeing the most outrageous amount of growth. So I think this is in particular a pain point right now in terms of automating data centers and in terms of the whole process. And so that's what I'm going to focus on today. But feel free in the Q&A or after, of course, to ask me about anything up here. So I'm going to get started here by talking about and defining what I call the modern data center. And when I say the modern data center, I think of something very specific, and that's what I'm going to define here. And I think this will be a nice transition from actually where Nigel was talking. I know a lot of people here, I was here, are still in physical data centers, and what I'm about to describe is not excluding that. So up until basically the last slide in this section, it completely applies to physical data centers, and everything I'm going to be talking about today applies to physical data centers. So it'll be appropriate, but there are cloud aspects to it for sure, because I think that's what you have to think about as you go forward, because I think even as Nigel said, the lines are pretty blurred nowadays. So I'm going to start at the very basics, but I'll move through them really fast. We'll get through this section really quickly. And there's no dates associated with anything, because depending on your organization, when you move from one thing to the next is different. But almost assuredly, all of you are sort of towards the end of this process. So to get started, we'll start with the very basics, which doesn't need any explanation. But just to show you where we start is one server. When there's one server, there's actually not a need for automation. Doing things manually, babysitting this server, writing scripts, keeping everything running is just not difficult. So you just do it. But really quickly, things blow up to multiple servers. But even in the small single-digit cases, you could manually do it and not really be a bottleneck and not really cause any friction. So again, we're not seeing a lot of automation problems here. But as we keep moving on, we get more and more complexity. So at some point along the way, we got virtualization. Hopefully all of us are at this stage. But virtualization confused things even more because we have VMs. VMs are on servers. VMs network a little bit differently. There's a lot more density, and automation becomes a lot more important here because where are you going to place the VMs? What address are things at? How do you communicate with them? These are questions you didn't have on a single server, but now you have. And so this is probably where a lot of people are today, and this is a pretty modern place to be. But of course, more recently, in the past couple of years, in terms of popularity in the past couple of years. The technology has been around, of course, for a much longer period of time. But in the past couple of years, containerization has really swept over. And so now we have a more complex view of things. And I purposely made it exacerbated the problem here, where you have containers, directly on servers. You have them in VMs. You have some VMs without containers. You have some servers without VMs. And it all, the answer of where do I put what is really, it depends. Like, is it useful to put it in a container? Is it useful to put it in a VM? Is it in the cloud? Is it in your interconnected physical data center? It's getting more complicated, but there's reasons for all of this stuff. But as we're heading into this sort of thing, this is where automation not just makes sense, but is effectively required, because you're either paying a lot of people a lot of money to keep this not on fire, or you're just not taking advantage of everything you can be. And I think this still applies to physical data centers. And the next slide is really the only one that doesn't. And so the next slide is really, I think, where we're heading towards, which is service proliferation. And this is something that in Silicon Valley is happening much faster than everywhere else in the world. I forgot who said it, but I wouldn't say it's a Germany problem. It's just everywhere else is really still being much slower with good reason. So, but as things are going on, we're seeing more and more things become services. And so, if you go back 5 years, and you ask someone, would you ever put X on a software as a service, where X is DNS or a CDN or a database for sure, a common answer from an operator would really be definitely not. Like, no way, no way. It's critical that stays behind our firewall, under our control. We cannot lose control of that thing. And as time is going on, the set of things where people are saying no to that is getting smaller and smaller, for a lot of reasons. Like, there's a lot of reasons, but today, even large companies rarely run CDNs. A lot of DNS is outsourced to people like Dyn and things like this. So more and more is becoming software as a service and infrastructure as a service. That, in terms of automation, these are things we have to think about, because if you can't deploy your application anymore without spinning up a load balancer as a service, then it's pointless to only have the Puppet necessary to configure your servers, because it won't get your application to the deployed state because you're missing the load balancer piece, for example. So this is sort of the end where I think of the modern data center. Is like, if you're building a tool today, you have to think all the way through to, okay, I could automate things now, but am I going to be able to automate these things in a few years, or as we head towards this? And to put it down into text and get out of diagrams, here's sort of the matrix of choices that you have in various categories today. So you have hybrid cloud choices, your physical data center, your private cloud, public cloud. You could be both. There's many different paradigms there in terms of just being a physical place, using virtual machines or using containers. There's all these IaaS things, and they're all useful in their own way, so they come into play. There's operating systems. This is definitely, without a doubt, compared to all of them, the easiest one to just standardize on, the easiest one to just be like, everything's Linux. But at some point, I still go into most companies, and they're like, oh yeah, we're a Linux shop. It's like, turn away from those 2 Windows machines running Active Directory, right? Like, shield your eyes. But still, like, having 2 or something is fine. Like, mostly the OS thing is pretty easy compared to everything else to homogenize on. But realistically, sort of as I'm going into places, I'm seeing a mixture of all of this. And so all of this needs to be automated. All of this needs to be managed, and it's sort of a mess. And a lot of people dream, I think the dream for everyone is for a homogeneous sort of infrastructure. And my opinion on that is that homogeneity is primarily a myth. You could reach periods of homogeneous infrastructure, but sort of admitting that you want a homogeneous infrastructure is admitting one of 2 things. The first thing you're either admitting is that you're going to pick something and you're never ever going to change, and that technology is never ever going to improve. Or the second thing you're admitting is that as the technology improves, you'll be able to make atomic steps into the next paradigm as things shift. And I don't think either is true. So I think as new technology comes and evolves and comes out, then you're inevitably going to have to change paradigms to something else. And so you might be homogeneous for a period of time, but then when something new comes out, you're inevitably heterogeneous for usually a much longer period of time. Nigel had a bunch of IT analyst quotes up here. I wish I had an analyst quote up here, but I remember reading in an analyst report that one of them, Forrester or Gartner, one of them, expects the Fortune 500 in the US to complete their virtualization transition this year. So, virtualization's been around since since Intel added the extensions in like 2004. So virtualization's basically been around for a decade, and the Fortune 500 should complete the transition this year. So it'll be pretty exciting to see them begin the transition to containers and complete it in about 2025. And during that time, they're going to be a mess. So, okay. So why do we have this complexity? Like I mentioned at the very beginning that the single server case was very nice. You don't need automation. You just have a person. They watch the server, and it stays up and running. But all that complexity is there for a reason, and it's very beneficial to us. And the benefit is that we get to move faster. We get to deliver and maintain applications much faster. And so I've shown this sort of slide a long time, but this is sort of how I like to break down application delivery in terms of 3 different categories. For some companies, these are silos, or for some they're not. But that's not what I'm trying to show. I'm just trying to show 3 different categories here of sort of stages things have to go, and then they usually spin around in a circle. But as I look at this, these are the things that people are optimizing for, and these are the reasons that this complexity exists. It's, as virtualization comes out, as containers come out, they speed up the deployment part, or they ease the maintenance part. And so they're making this easier, which makes application delivery faster and faster at the expense of management complexity. But that expense is usually worth it. So the one quick pitch is that this is sort of how we categorize our tools as well. So this is sort of where they fit into. And so today I'm going to be talking about Terraform and Consul in there. So focusing on the deployment and maintenance side of things and looking at that. Deployment and maintenance is at its most fundamental level 4 steps. There's the acquisition step, the provision step, the update and destroy step. Acquisition is get the hardware that it's going to run on. Provision is make it ready to run my application and put it on there. Update is incremental updates of an application, and destroy is decommissioning the whole thing. And normally, it does acquisition, which is relatively slow, provision, which is a little bit faster, and then update and provision sort of spin in this hot loop for years, and then you decommission it at some point. If you read about immutable infrastructure, it's this without any loops in it. You just kind of go through, skip step 3, and you destroy, and then you go around the whole thing. But this is the most general view of sort of deployment and maintenance. And historically, acquisition has taken a long time. Provisioning has taken a little bit faster, but still a long time. And we could assume SaaS doesn't exist in terms of this history. And that's where we came from. Acquisition, getting a server was ordering from a vendor, or if you pipeline the orders really well, it's waiting for them to get racked up, plugged in, ready to be provisioned. That sort of thing was slow. Provisioning took hours or days. Thankfully, people like Puppet have solved that problem for us, and SaaS didn't exist. So today, everything is pretty much instant. So everyone here is still in physical data centers, but even in physical data centers, you could get this pretty much instantly due to the sort of increased amount of things like OpenStack, opinions aside on the quality of that. But you can make physical data centers instant in terms of hardware acquisition. And provisioning is minutes now, again, thanks to things like Chef, Puppet, or pre-baking images of things like Packer. And then SaaS also is minutes. Almost every SaaS out there that's worth using has an API. So you could click on a dashboard and get the plan you want and all this stuff. But most of them, you could also automate it. So everything can be done in minutes. And imagine the scale that we're at today. The scale you're at right now is probably dozens to hundreds to thousands of servers. And if you imagine that you could go through that acquisition, provision, update, destroy cycle in minutes, thousands of times, it becomes just so obvious that a human being can never take full advantage of this situation that we have. We're given the ability to manage everything in minutes or seconds, and people just don't move that fast. And people don't move that fast 1,000 times in parallel. So if we want to move as fast as the technology is moving, we're going to have to use automation. The final, my one last step back into history before we just go through into some tooling, is just properties of the data center and how those have changed. So historically, there's been a relatively fixed set of servers. And I'm not saying the amount of servers that are racked. I'm saying the amount of servers sort of in use or that you're provisioning. So historically, there's just a relatively fixed set. You're not moving that much. There are fewer applications to deploy. You know, SOA has been a thing for a long, long time, but SOA historically has been an enterprise thing. When you're an enterprise, you start thinking about service-oriented architecture, middlewares, like that sort of stuff. But now, you know, with a ton of companies out there tooting the microservices horn, which is service-oriented architecture for startups, we're getting a lot more applications to deploy a lot earlier on. That sort of needs more servers or needs more management or automation or both or all of the above. There was fewer SaaS before. That's sort of, we've been talking about that. And then there's just less demanding web traffic. And this is sort of a funny bullet point because it's kind of sad, but it's just a fact is that, you know, there was just less internet connected devices. There was less robots hitting your things. It was usually humans in a browser. And now we just have to serve traffic to a lot of stuff that doesn't actually see it. Even APIs and stuff. There's just more and more stuff that we have to respond to and generate a response for. So today, yeah, everything's elastic, SOA, microservices, etc. There's a SaaS for everything out there, so we have to at least think about it. And then more internet-connected devices, more people, however you want to look at it. No matter what, there's just factually more web traffic out there. It is split among a lot more websites, but if you're sort of a big player, you're just getting more traffic than you were before. So what do we need to take advantage of this? I already mentioned that in terms of speed, you need automation no matter what. But what properties do we need from that automation? I like to say that you need to get 0 to deploy or 0 to something far in one command. You need to get as far as you can with just one command. Because more commands means a person's coming in more often. If you have one command, that's pretty much the minimal you could go. Even if it's a fully automated system, at some point someone kicked it off. So that's one command. But you really want the person to come in, review something, hit a button, and let it go and be confident that it's going to work. You need resiliency through distributed systems for the core of your infrastructure. Nigel actually did a great job here, which is just that as you get more and more infrastructure, as you treat more infrastructure elastically, you just have to assume that most of it's unreliable. And a lot of people I've found in terms of physical data centers think of this as a binary thing. Like you have to think of it as completely unreliable or completely reliable. But for the most part, you could still, if you have those services that just, they were written 10 years ago and they're super single server and just can't ever go down, you could still just pet those servers and keep those servers really reliable and just flag it as such. And you could just say that the rest of it, you know, all the other machines, everything else can be automated, this one can. And that's a very valid sort of transition point towards more automation. So you need to treat things as unreliable, and for unreliable things to work, at their core, they really need to have more distributed systems. And I'm not saying you need to use a distributed database like Reoc or something, but you need to have a good setup in terms of high availability. You need to have certain distributed systems like service discovery, which is my own bias pitch here. But I think more and more as time goes on, these core tools will be distributed. You need some level of self-healing. Auto-scaling, auto-healing is sort of the buzzwordy way to say it, but you need some level of, if it's unreliable, you need something there that'll punch it back into action, or you're going to be getting called, paged all the time. So you just need something that can know if something's okay and to spin something back up. Auto-scaling in terms of growing and shrinking is sort of icing on the cake, but you just need something that will make sure things are at a minimal healthy state across the board. And then you need better teamwork through codified knowledge or sharing. As things grow, as things scale to a higher number, as you get more people, you can't have the one person who knows everything anymore. You really need to share knowledge and make sure you can work as a team. And also delegate. So developers want to do more things on their own. As operators, we could fight that as long as we want, or we could come up with a way to make them happy, or at the very minimum, give them the illusion that they have some control, while making sure that we control at the end. But like that's sort of an evil way to say it. But like you should be working together to make something work rather than just fighting it. So automation, we're going to talk about these tools. Let's get on with it. Okay, so let's go straight into tools. The first tool I'm going to talk about is Terraform, just because it makes sense in that order. You're deploying first. Terraform's helping you get that deploy out. And then we'll talk about Consul after. Both of the tools are completely open source. There's no enterprise versions, nothing like that. So that's that. If you want to learn about it, the URLs are in the bottom corner. So Terraform, in one sentence, is a tool to build, combine, and launch infrastructure safely and efficiently. And not just infrastructure, but applications and things like that. And we'll get into that. But this is the very dense thing. The more practical questions that Terraform answers are these. So if I, your boss, a manager, came to you and asked you to create a completely isolated secondary environment to run an application or a set of applications, staging, QA, etc., what would you do? How would you do it? How do you deploy or update a complex application, something that's not extremely trivial, but doesn't have to be very complex, just not the most trivial? How do you document how the infrastructure is architected? This gets more tricky as services come in, especially. What talks to what external services are needed when at what point in the data path, that sort of stuff. How do you document this? Well, I'll get to the answers after this. And then finally, how do you delegate some of the operations to these smaller teams, whether they're developers or just not external, but operators that are on development teams that are outside of what I like to call core operations? How do you delegate that sort of stuff? And in terms of Terraform, these are sort of the answers you give it. To create isolated environments, it's one command. To deploy and update applications, you code it, infrastructure as code, you diff it, see what's going to happen, and then you apply it. You treat it sort of like an application. How do you document how infrastructure is architected? You could either read the code. I should change that answer because it's not the greatest, but you could either read the code or Terraform could generate you a graph. And the graph shows you how everything depends on each other and what references what. And we use that in order to find, to predict sort of disaster recovery scenarios. You should always do disaster recovery exercises, but the graph could help you be like, well, a lot of arrows are pointing to this one circle. And you could use that to try to break it up or just understand what that means for you. And then delegation, modules and code reviews, we'll get to that in a second. So the specifics of how in terms of Terraform. So these are the bullet points of what Terraform does for you. It allows you to create infrastructure with code, and not just infrastructure in the config management sense. We're not, actually, Terraform at all is not trying to encroach on the config management space. We're not trying to install packages. We're not trying to set up users and things like that. But what Terraform does do is build the actual infrastructure. It launches servers, it bootstraps servers for things like Chef and Puppet, but it also handles non-compute things. It'll set up load balancers, network devices, software as a service, and then it could layer within that. So you could pull from Foreman, set up OpenStack on top of it, then configure OpenStack, set up VMs on top of that, then pull from the VMs, install Docker on top of that, and then deploy containers on top of that, all in one command. It could do the whole layering. Yeah, one command to create and update infrastructure. Preview changes to infrastructure with plans or diffs. There's a whole section to that, but that's really important to infrastructure, to Terraform's functionality, is being able to know what it's going to do before it does it. Using that preview functionality with code and with normal text diffs, you're able to see, treat infrastructure more like an application. You're able to code the changes you want to see in infrastructure, see exactly what would happen. Not just this line was added and this line was removed, but actually see Terraform be like, this is the server that'll be created, this is the server that'll be destroyed, this is the order that it'll happen. You're able to see that sort of thing, and then apply it all at once. And then finally, you could break down your infrastructure into distinct modules or components. Use that for delegation, teamwork, sharing. You could create modules that people could reach into and modify the infrastructure. You could create modules that people only see the outputs from, so that they're never allowed to mess up the infrastructure. And I'm going to talk about both of those. So the infrastructure as code side of things looks like this. Here's an example of a Terraform configuration. The syntax is one we made up on our own, but similar to something like Puppet. But really, this is just JSON syntactic sugar. It also accepts JSON, so that's sort of what it looks like. But this is Terraform creating two things, a DigitalOcean droplet and a DNS simple record. But it could also be OpenStack. It could also be Foreman. It could also be Azure, Google, sort of a lot of other things in there. On the top, we're creating the DigitalOcean droplet. It should be pretty straightforward what's happening here. At the bottom, we're creating the DNS record. One interesting note is that the DNS record is referencing the IP address of the DigitalOcean droplet. You could sort of see the syntax there. And this is very different from I think, most other config management systems out there in terms of how we model things. So any resource could reference any attribute of any other resource, basically. So that IP address isn't a variable. It's not coming from some operator configured thing. It's just something that was computed as a result of creating a DigitalOcean droplet, and now we could use that value later. And that's really important to making this work. So it's human-friendly config. It's JSON compatible. In practice, we see most people using the human-friendly version and then using JSON for automation, scripts generating configs. That's mostly for auto-scaling, that sort of stuff. But the point is it's flexible. It's text, so you could version it, and you should. You put it in version control. You treat it like code. Nothing weird there. It's declarative, very similar to something like Puppet. I think that at a certain scale, declarative makes a lot more sense than imperative. And for infrastructure, it's really hard to make things imperative because as it grows, you just can't actually reason about the dependencies. And so declaratives, I'm very opinionated about declarative all the time. And then this last one is sort of marketing, but like infrastructure as code in a way not possible for. What I mean by that is that you could reference anything in your infrastructure that you want, not just in the scope of sort of a single machine. And you could also add your own custom resources there. So the most unique sort of thing I've seen is that Yelp, I think it is, they created their own custom resource that commits to Git. And that seems like the craziest thing ever. And that's what I said when I did it. I was like, why would you create a resource that takes a value from something and commits it to Git? And it's because they have legacy things where they have a script that puts Git into a ticket system for the machines they can't automate. And they're like, well, at least we could automate everything and then push the data automatically to the things that can't be automated. And I was like, hey, like, fine. But at least you could do that sort of from one thing and not a crazy way. It's one resource. It's doing one create, read, update, delete cycle. Each one of these resources has their own acquisition, provision, update, delete cycles, and that's really what Terraform's doing. Okay, so once you have that config, you get 0 to done in one command. So this is very not exciting. You just run apply and it does it. Did it in the right order. What's important about it is it's idempotent. This is really important for something like Terraform because it doesn't matter if you're just using something like AWS. At a certain scale, AWS APIs just will fail you. So Terraform has to be idempotent. I think Terraform will retry for you, but if without the retries in there, if I run Terraform on something with a 500 resource AWS thing, it'll get a 500 every single time. And so it's idempotent. If something fails, you just run it again. It'll only do what isn't done, and it'll get there. But most of the time, it does it in one command because of retries, built-in retries. It's highly parallelized. Again, a really important aspect for something like this. So a lot of config management systems are parallelized. Some aren't. They could get away with it because serially installing stuff onto a machine isn't that slow, but serially creating servers, bootstrapping them is really, really slow. And so it has to be as parallelized as possible, and Terraform does that. And we'll only do what the plan says, which I'm going to just talk about next. So for the plan, this is what a plan looks like. And you just run the Terraform plan command to get it. It looks like a diff, and the plan tells you what Terraform's going to do. So you can see on the top here it says plus DigitalOcean droplet. That means it's going to create it. It didn't exist before. It could also say minus. It's going to delete it. Minus/plus means it's going to delete it and then create it. Plus/minus is going to create it, then delete it. Or a tilde, which means it could do an in-place update. You can see all the attributes it's going to know about. So you could see the stuff you configured, but you could also see a lot of things that say computed. So Terraform actually knows what it will know once it creates the thing. So this is also a different architecture than a lot of config management things. And then you could also see how things relate to each other, and then the ordering things are going to happen. And that's that. The important things about plans is they show you what's going to happen, and then you could save them to guarantee what's going to happen. And so this is very different than like a dry run or no-op mode. And it's not negative against them. They're very upfront about what those things mean. But Terraform's a different model. It shows you what's going to happen given the current state of the world, and then you could save that. And what you're saying when you save it is, it doesn't matter if the state of the world changed, just do what this plan says anyway. Like you said, you were just going to change the image of this machine. Even if the source image is different, just do what you said you're going to do or try to. And what Terraform will do is try to do it, and then where things mismatch, it just won't do anything at all. So if it reaches a point where the plan, given the current state of the world, given the plan, it cannot do what it said it's going to do, it just won't do it at all. And then plans show reason for certain actions. So the big benefit for this is, again, something like CloudFormation. Those sorts of things, you just apply it, and then it's going to do something. But you don't know what it's going to do, and sometimes what it does is destroy things and causes downtime. And they document out what changes cause that sort of downtime, but it expects that your operator knows that effect for every potential change that's going to happen. And basically what that causes is you need one super genius that understands the full scope of not only your infrastructure, but how, in this case, AWS works and how your changes are going to interact with that system. And it doesn't scale at all. Like the amount of knowledge required to be safe with something like CloudFormation is just not organizationally scalable. So with plans, for example, if the DigitalOcean droplet existed and I changed the image, you can't change the image of a machine without destroying it and recreating it. So next to the change of the image in parentheses, it would say forces new resource. So you'd be able to see that specific change is what's causing it. And then when you look at the plan, you could say it's 2 p.m. on a weekday. I don't really want to do that right now. You could change that and make sure you get fully in place updates. There's also flags you could give to Terraform to say, do the changes. But if there's anything that's not in place, then fail. So you can make sure that happens. And that's plans. So the general workflow that Terraform has is you make code changes for your infrastructure, you run a Terraform plan, you do a pull request or open a ticket or something with both the code changes and the plan, and then someone comes in, reviews them, a couple people review it. When you're done, you apply the plan, exactly. And this lets you treat your infrastructure a lot more like code. It keeps a history of the original state, the destination state, what Terraform actually did, that sort of thing. And it makes working on a team with infrastructure a lot more of a possible even experience. And then the last thing is knowledge sharing or teamwork. And this is done through modules. So here's an example of a module. Up here, we have a Consul module. And this one actually works. Like if you copy this module into your file and ran Terraform apply, it would actually create a 3-server bootstrapped Consul cluster on AWS. We also have other cloud platforms in there, but this one would be AWS. And then we're taking the down here, I didn't highlight it, but we're taking the address out of Consul to use it. So you could imagine that your core IT team or ops team that knows how to create a safe, secure, scalable piece of or component of infrastructure, like a RabbitMQ or a Postgres or something, could create a module for it and give it to developer teams and say, you manage your own infrastructure, but never ever create your own Postgres cluster outside of this module, because this is the way we do it, and this will make sure it's backed up and that sort of stuff, and that lets you do that. And you could go one step further. So modules will create their own instance for everything. If you give it to a developer, they'll create new servers every time. You could go a step further and use the syntax is a little weird, but we call these remote modules, but remote states, remote modules. And you could actually reference modules that other people have spun up. So in this case, we're referencing a Consul remote state and grabbing its address from it. And this will not manage the servers. So in this case, what core ops would be saying is we've spun up the highly available, backed up, long-running Postgres instance that we're on call for. You could use it, but you're never allowed to touch these servers. Nothing related to the servers. And so we could access the outputs. This run will fail if that's not up. So you could safely share things that you don't want people to spin up either. So modules are self-contained infrastructure components, allow delegation. Some teams create modules, some teams consume them. And the general real-world breakdown we've seen is that as people try to give developers more power, as people try to scale with a service-oriented architecture and developer teams doing their own operations, every company I've ever really gotten into maintains their core operating team, which knows how to maintain things like OpenStack and networking and physical machines. That knowledge really never reaches developers because it's a lot of domain knowledge. It's not very exciting. But in terms of consuming that hardware and spinning stuff onto it, usually does. And modules are a nice way to let people use that. So this is sort of a summary of everything. But what Terraform does, the bottom bullet point here, what Terraform does is gets you from point A to point B with your infrastructure, and it doesn't keep running. It just, you run it, it does its job, and it exits. It's not a long-running server daemon or anything. So what we like to say is that it's a static tool from getting you from point A to point B, but you still want some dynamic real-time tool to always be running to make sure that things are healthy, you can find them, that sort of configure them, and that is Consul and what I'm going to talk about next. Okay, so Consul, here's its one-sentence description. It's basically buzzwords separated by commas. So the practical thing, here's the things that Consul could actually, well, it could actually do everything in the previous slide, but here's the questions that you would practically be asked that it could answer. Where is a service? Is that service healthy? What are all the machines that I currently have running? What is the configuration of a service? And also leader election and locking. So in a distributed system, you want to make a script might be killed instantly, but you want to make sure that only one thing's doing something at a time. Consul helps you say you 3 servers run the script, but actually only one of you do it. And Consul will facilitate the leader election. So this is incredibly important in this elastic sort of environment because you can't hard code IP addresses anymore. Things like config management for a service discovery solution becomes too slow because you don't want to wait 10, 30 plus minutes for a convergence across your entire data center to get the right values. So you need something a lot more real time. So service discovery, where is service foo? And more practically, your web application, where's the database you have to talk to? Where's the queue? That sort of thing. In terms of the Consul world, we expose this out as a DNS record or the HTTP API, but DNS is almost always used instead. And that lets you no application has to know about Consul. If it knows about DNS, it knows about Consul, which is basically everything. So you discover services by putting their name, .consul. Consul returns you the list of services that are currently running with that name. The DNS is legacy friendly, like I said, but if you want a ton more data, you could use the API directly. But in practice, for everything other than maintenance and monitoring scripts, you never really need the HTTP API. And you could discover both internal and external services. So this is going towards that modern data center thing I brought up earlier. That dig, that DNS lookup, could return private IPs in your data center. Or maybe your database is a software as a service. That might return a CNAME to that software as a service. But you could register both with Consul. So you could both do private things and external things, and that's an important consideration in terms of, as time goes on, if we move to more services, do we have to change this tool? And in terms of Consul, in terms of service discovery, you don't have to. Failure detection. So what you really want to do is ask Consul, where is the database? But you don't want Consul to give you an IP that is stale, that it knows it's gone, or that someone knows it's gone. So failure detection is both a way to detect failures, as well as affect the service discovery, so that when you're saying where's the database, you're actually saying where is the database that at this point in time you're confident that I could reach. So there's no good screenshot for failure detection, but basically what it is a Nagios compatible executes a script, exit code, non-zero is unhealthy, 0 is healthy, and you run it against services and machines, and Consul also detects if the machine is down in terms of a network partition or something. So if there's any sort of failure of a service or the machine the service is on, it won't be returned from DNS. So if you dig it, it won't be there. But you could always look in the UI, which is the screenshot before that I just blasted through, or the HTTP endpoint, which will return the full catalog and the full health states of everything. So then Consul's key value storage. This is for the purpose of configuring services, and there's interesting questions around this that people adopting Consul usually have, which is, what's the use case of this versus something like config management? Let me first show you what it looks like, and then I'll answer that question. So you just store things and get things using a HTTP API. Really simple. Anything could do it. You don't need a client for Consul. You just need an HTTP client. And you could grab and put values. The storage is highly available. It's really hard to take out the storage of Consul. And here's where it gets interesting. So what do you put in here versus putting in a config management system? What I like to say you put in Consul is any knobs you have for anything. So you want your config management system to put down basically the template for how Apache is configured, how your application is configured. You want it to put down the file. But anything dynamic in terms of how many workers, what port are we listening on? Is it on or off? Is it even enabled? All these little knobs that you might want to ever turn, you throw it in Consul. And the reason you do that is it makes a push versus pull model. So with Consul, you're able to watch keys for changes and act on those changes really quickly. And so when you turn a knob, when you say turn maintenance mode on, you're not saying turn maintenance mode on and wait 10 to 30 minutes for it to converge across a cluster. You're saying turn it on, and within hundreds of milliseconds for thousands of servers, it's taken effect. It's just happened. And so this is where it makes a lot more sense. You're able to do ACLs and encryption on these things, so you could put more sensitive information in there. Consul's not really made for something like secrets, but in terms of sensitive information, you could put it in there and protect it. And that's really what the configuration is for. And then multi-data center. So a lot of software today, well, let me step back. A lot of people today, organizations, are becoming multi-data center faster than ever before. Multi-data center used to be a very high-scale thing. With things like AWS, you could be multi-data center with a few clicks. If you're using software as a service, you're not really sure what data center things are in. So you're sort of multi-data center very quickly. And a lot of software today is giving you some software that's pretty good and then saying, oh, you're multiple data centers, figure it out. And they're not giving you any really good information to get there. And what this forces you to do is build into your applications, choosing between data centers, putting clients into them, something. But with Consul, we handle multi-data center for you. It doesn't require any different configuration on the client side of things. Application still just works, and here's how it looks. So from a DNS discovery perspective, you just put the data center you want in the query. So you could ask for web front ends in 2 different data centers, and you'll get 2 different responses. So, excuse me, again, you could configure an application to use service discovery and something in another data center, and it still doesn't have to know about Consul. If you leave out the data center, it assumes the current data center. For KV, you could specify data center 2, and it'll write to different data centers. So you could have different configurations, different knobs in different data centers. We also have a tool that lets you replicate data to other data centers if you want. So that's it. But it's very simple. But that simple interface lets you just use it from any data center and communicate with any data center without any additional tooling, networking, etc. than you normally have. So all this, and the last bullet point is really nice too, which is that if you use the Consul UI, you could view all your services, all your configuration, all your machines in one UI. There's just a drop down for what data centers you have, versus the other response, with something with a lot of other tools out there, which is, just run one UI per data center and figure it out. And you don't have to do that with this. And then sort of the last feature, I think the last feature I cover with Consul is orchestration. So Consul on its own isn't a very high-level orchestration engine. It's not made for that, but it gives you these low-level tools to build orchestration on top of it. And the tools are events, exec, and watches. Here's what they look like. An event's at the top. An event is a very lightweight, fits in a UDP packet thing that's sent out over the network. These are really high scale. You'd have to send millions really to see them even on any network graph. They're really cheap and just go out there. Watches are a sort of complex thing that lets you watch events, lets you watch changes in Consul, when a service becomes healthy, when a service comes online, when a machine disappears. There's any sort of query you want to put in there for a watch. And then when that happens, it'll execute a script for you. So in this case, we set up a watch for that event we just fired. So when the deploy event goes out, run the deploy script. It'll get sent the payload on standard in, and you do something. And then finally, there's exec at the bottom. So exec is targeting, in this case, web services. You can target machines and to run a script. And that really scalably runs a script in parallel across all the machines that matches, and then puts the standard out, standard error, and exit code back into the key value store for you to consume any way you want. The difference between exec and event, event is asynchronous, exec is synchronous. Event happens over UDP, so it's probabilistic. Exec happens over TCP, so it's for sure going to make a connection or error if it doesn't. So you just have two different trade-offs there. Exec is much more expensive. Event is much, much cheaper. But it's up to you to choose what you want to use, depending on the situation. For a deploy, you probably actually don't want to use events, but you could do whatever you want. And so Consul gives you these powerful orchestration tools. There's pros and cons to each, but you have the power to choose. And when we first came out with Consul over a year ago, we really stressed the pros and cons in terms of scalability. But since it's been out a year, we've basically seen that every one of these approaches scales to many, many thousands of agents, running them pretty often, up to once a second for some of these across thousands of servers. And so from a scale perspective, I wouldn't worry about it until you're really, really big. We'll skip this. So the workflow with Consul and Terraform together is generally that the servers started via something like Terraform, and they're started just in parallel in any order you want. The database doesn't need to start before the web server or nothing like that. You just start them. The Consul agent is started, it joins the cluster, and then when the services come up and they become healthy, they show up suddenly on DNS. The application picks it up and starts running, and sort of everything eventually comes together. So you get rid of a lot. If you fully embrace something like Consul and Terraform, you get rid of ordering dependencies. You get rid of fragility with that, because you're just using DNS. If there's no responses, you handle it in some way. An error message that you're down, or you just restart your process over and over. But what you eventually get with Consul is that as things come up, very quickly they converge into a running thing, and that's really nice to see. So operational bullet points between Consul, because since I'll try to just cut off a lot of questions here that people would have. I've given a whole talk on the operation of Consul, and not because it's complex, but because there's a lot of nuance to it. But here are the main high-level things that are important to understand. So Consul servers do leader election via Raft, but you run an agent on every machine if you want. The agent's optional, but highly recommended. It's how it does failure detection on a single node scalably. But Consul servers, you run like 3, 5, or 7, and they do leader election. It uses a gossip protocol for liveness checks. It uses a gossip protocol called Swim, if anyone's heard of that, but it's a very, very scalable way to both send small amounts of data, like events, but also do failure checks. So as your data center grows, it grows linearly with respect to how expensive a liveness checks cost versus versus a square approach with something like heartbeats. There's 3 consistency modes for the data. So there's default, which I like to just say is pretty much consistent. And what that means is that it verifies a write is done before it returns the data. But if after you send data, there's a network partition, and it's complicated, but if after you write data, there's a network partition, and it gets what it thinks is a majority, but there was a leader election while there was a partition, it's no longer the leader, then you'll get back a stale value by a few hundred milliseconds. For those scenarios, it's mostly okay for most applications, but if you really, really care that it has to be the correct value, you could choose consistent. If you choose consistent, then every write will consult every server no matter what, not just the majority. They all have to return that you are indeed the leader, and it'll return it. Or you could do stale, which won't consult anyone. It'll just get the value that you want, which is pretty good for scalability for a lot of keys. But default is pretty consistent by default. There's encryption and ACLs across everything. So the gossip protocol is over UDP, so it uses a symmetric key, and then the API and the TCP stuff is all done over TLS. So there's encryption across everything, and then there's ACLs across most things, key value and services now, and we're adding ACLs across exec soon. And real-world usage today for Consul is up to many thousands per data center. I think our biggest deployment in terms of data, one single data center is 20,000 servers, but the vanity metric that we're able to say now is over 50% of all North American internet traffic goes through a machine running Consul. So it doesn't take a lot of organizations to get that metric, but it does take a lot of servers. So Consul's used at pretty high scale and is running fine. So that's everything, and thank you, and I'll answer any questions. All right, thank you. Are there any questions? I'll start with this. Okay. Yeah, it's not released yet, but we have a Terraform provider for Foreman. When it's almost done. It's just being tested right now. Maybe next week, maybe 2 weeks. I don't know. Yep. So like I mentioned with the ACL, so there's ACLs, but I mentioned briefly, but they don't cover events and execs yet. So you could just disable them cluster-wide, and they couldn't really compromise that unless they gained control of a majority of your servers, not all your agents, but the servers. But you could just disable them, and for everything else, for who could see what services, like you could say that web machines can never, ever, ever discover query where, I don't know, certain data nodes are, like that sort of stuff. You could partition that up, and the key value as well. So you could say those machines can only access web configuration. They can never see the database's configuration and things like that. So across KV and service discovery, there's ACLs that you could put. But across the orchestration stuff, there's not yet ACLs, but they're coming in not the next release, but the following release. If they're not disabled, yep. Any other questions?
Do you have dependencies in Terraform? So from one service to or resource to the other one?
Yeah, so we do. The dependencies for Terraform are mostly implicit. But not in a magical way, just in a very obvious way. Like if the DNS simple record is clearly using the DigitalOcean droplet, so Terraform will create a graph edge for you to make sure that the droplet happens first before that. But you could also, if there's a not obvious dependency, like if you have an application that just will crash if the database is not running, even though it doesn't use a value when you're making the server, you could set a specific dependency. So you could say that that server has to be up and running before this one starts, and you could just tell Terraform that exactly. Yep. Any other? Yep. Yeah. So the question is there a syntax dependency check? So Yeah, there's a syntax check for just the syntax, but it has to turn into a directed acyclic graph. So we check for cycles, and we check for some other like edge cases. But yeah, you can't get into an infinite loop, for example. Yeah, it'll be so if you remove the first server, it'll be an error. It'll do it's a lot like a compiler. It'll do a basically lexical pass in order to compile everything into an AST, which is sort of similar to a graph. It's not its final graph form. Then it does a semantic pass over all the graph nodes, verifies things like you're accessing properties that exist, resources that exist. There's certain types of variables you can't use in certain things. It does that. And then it finally does a transform into a graph, a full executable graph that it then executes. Yep. Yep. So the order comes from the graph. Yeah. Anything else? I think that's good. All right. Thank you.
Thank you.
Okay. Next week. Yeah. It's done. It's all done. I don't. I know, but I can't tell you.
Okay, thank you very much. Impressive stuff. Thank you.
Thank you.